So, hang on one sec. We didn't quite finish this section, so we will continue this, these notes on Wednesday. I'm probably going to have to move your homework back because of that. So I know. I'm so sorry. Don't worry about finishing Wednesday. Continue our discussion here on precipitation and equilibrium involving that. So let's now look at how our calculations of equilibrium involving the formation of a precipitate. So we're thinking about if we have two different solutions containing anions and cations of a particular type, we mix those together, will a precipitate form? And when we think about whether a precipitate forms, we'll think of some general compound AX, the solid phase in equilibrium with A, the cation and the anion, in the aqueous phase. And so we're saying that if a precipitate
He's not a fan of walking.
Adorable. Well, who would, I mean, if I had someone who could carry me and I didn't have to walk in the rain, that'd be great, right? Take that. Anyway. All right, so we're saying the question of whether a precipitate forms is essentially, is a reaction reactant favored or product favored? So if a reaction is reactant favored, that means we have a solid, so which is essentially saying that a precipitate forms. Okay. Reactant favored means the precipitate, which we usually abbreviate PPT, forms. In this case, PPT is not PowerPoint. If the reaction is product favored, the products are in the aqueous phase, that means that no precipitate forms. Okay? So that's sort of the distinction here. We're still working with equilibrium. We're still thinking about whether a reaction is reactant favored or product favored. Nothing has changed. Now we're just saying, okay, if it's reactant favored, that means that a precipitate is forming. If it's product favored, there's no precipitate that forms. Okay? So let's imagine mixing two solutions, 100 milliliters of a potassium chromate solution and 100 milliliters of a silver nitrate solution. Both of these go into a new beaker, total volume now of 200 mils. All right, so thinking about that means we're going to have a dilution equation problem here soon. When we're saying does a precipitate form, again, we're just asking is a reaction is an equilibrium reactant favored or product favored? Another thing here I wrote is remember the solubility rules. So potassium salts are soluble. That means that K2CrO4 is going to completely dissociate into 2K plus CrO4 2 minus aqueous. Complete dissociation there. And then we have our silver nitrate, AgNO3, is going to completely dissociate into the silver ion and the nitrate ion. All nitrates are soluble. Okay. All right, so we need to figure out, we don't really know what a possible precipitate is. It's not given in the problem. And so what we're going to essentially do to determine the precipitates is do a double displacement reaction. You may remember this from a 1210 course, but essentially we're going to mix the cations and anions. So we have originally had the potassium chromate. We can think about taking the cation, the potassium, combining that with the other anion in solution, which will be nitrate. So KNO3. So what do we know about that? It's soluble. All nitrates are soluble. The other possible thing that could form is with our other cation, the silver, and the chromate, CrO4, and that's a 2-, and the silver is a +1, so we need to have Ag2CrO4. And this is, in fact, an insoluble or slightly soluble salt. You could look up a KSP value for this, and we will do that soon. So effectively, this question is saying, will silver chromate precipitate when you combine these two solutions together? Okay. In order to solve that, we're going to set up a Q expression, just like K. We're going to do QSP, and we're going to compare that to KSP. So again, just like we did in our equilibrium chapter, compare Q to K to see if we're reactant favored or product favored, or see if we need to go towards the reactants or products in order to reach equilibrium. So let's look here. Let's start with the problem again. Same problem. Will we form Ag2CrO4? So we're going to write our equilibrium for that solid. It's going to form 2 silver ion and CrO4 2-. Oops. Okay. And the KSP for this equilibrium is 1.1 times 10 to the minus 12. Times 10 to the minus 12. We're gonna use that in a little bit, okay? All right. So what we first need to do is calculate Q. We set up Q just like we do K. We're going to have our silver ion squared because of the stoichiometric coefficient of 2 times the chromate ion, CrO4 2-. And we're going to calculate what Q is, given the concentrations that are stated in the problem. So we're given a concentration of 1 times 10 to the minus 3 molar potassium chromate, and 100 mils of that, and 100 mils of 1 times 10 to the minus 3 molar silver nitrate. So again, we're combining these into one flask or one beaker and seeing if we form a precipitate. For our chromate concentration, okay, we have 1 times 10 to the minus 3 moles per liter of K2CrO4. We know that for every 1 mole of that, we get 1 mole of CrO4 2-. And so the concentration that we start with of potassium chromate is equal to the chromate concentration in the original solution. But then we're going to take that and dissolve it or mix it with another 100 milliliters of solution. So we have a new total volume of 200 milliliters. So we need to use M1V1 equals M2V2 to figure out the concentration of chromate in the mixed beaker. So our initial concentration is 1 times 10 to the minus 3 moles per liter. Our initial volume is 100 milliliters or 0.1 liters. we want to solve for M2, and our total volume is 0.2 liters. So M2 is equal to 5 times 10 to the minus 4 moles per liter. That doesn't look like a 4. Okay. Everyone okay with that? So we're going to take this concentration and plug it in to our QSP, but we're going to solve for the silver ion concentration before we do that, and then we can do it all at once. So then our silver concentration, what does it change? I don't know. Silver concentration, 1 times 10 to the minus 3 moles per liter of silver nitrate. That's 1 to 1 with the silver ion. And again, we're diluting 1 times 10 to the minus 3 molar of the silver ion. We have to start with 0.1 liters of that, solving for M2, 0.2 liters total. So it's the same. 5 times 10 to the minus 4 moles per liter. Oops. Okay. So now we can, excuse me, now we can plug these concentrations into our Q expression. Okay? So we're going to have 5 times 10 to the minus 4 squared times 5 times 10 to the minus 4. And we're going to end up with 1.25 times 10 to the minus 10 for Q. Everyone okay with that? Questions? Okay, so now we need to, in order to answer the question, we need to compare Q to K. Again, Q is 1.25 times 10 to the minus 10. K was 1.1 times 10 to the minus 12. So QSP is greater than KSP. And so in order to reach equilibrium, are we going to form reactants or products? Reactants. Yep. Q is greater than K. That means we currently have more products than are needed to reach equilibrium. So we're going to form reactants, which means that a precipitate does form. Do we need to walk through that one more time, that reasoning? Yeah. Okay, so we calculate Q. Q is greater than K, which means we have more products than that would be required to reach equilibrium. So we need to basically form reactants in order to reach equilibrium. In forming reactants in this type of problem, the reactants are all solids, right? In forming that reactant, a precipitate will form. We form a solid. Make sense? Questions? Yes? That would be something you would either look up or be given in the problem. Yeah. If you're doing, if you're doing mastering homework and you're not given a K value, but you think you should, they probably want you to look it up in a table. Other questions? Yes. So you said if we need to form products to reach equilibrium, do we still precipitate? If we have a problem where we end up where Q is less than K, we need to form products in order to get to equilibrium. Depending on how much solid is in the beaker, you might still have solid left over, but we wouldn't say that a precipitate forms. We would say that a precipitate doesn't form. Good question. Anything else? All right. Let's do another slightly different but similar problem. I think this might have been from a practice exam. So you have a solution that contains the nitrates of lead ion, silver ion, and tin, each with a concentration of 0.01 moles per liter. And all of these form insoluble salts with the iodide ion. So we're going to have a total concentration of iodide of 0.0010 molar. Based on that, so the concentration of these ions of 0.01 molar and an iodide concentration of 0.001, decide which of these salts could form a precipitate. So we have our KSP values. So essentially you're asked to solve QSP for lead iodide, silver iodide, and tin iodide. And figure out, based comparing Q to K, which of these could form precipitates. Okay? This is the last problem times 3. But we don't have to do any dilution equation, so that's nice. So go ahead and work on that for a couple minutes. We'll check back in. it's best to write out the equilibrium, then write out the QSP expression. So QSP for the lead iodide is equal to the lead concentration, Pb2 plus, times the I minus concentration squared. For silver, it's equal to the concentration of, or excuse me, for silver iodide, equal to the silver ion times the iodide ion. Nothing squared there, everything's 1 to 1. And then for tin, QSP equals tin 2 plus times iodide squared. And now we can plug in our concentrations that we were given in the problem of the metal ion and the iodide concentration. So for the lead, well, each one of the metals is 0.01 moles per liter. I minus, we get 0.0010 squared. And so we calculate QSP for the lead iodide. We get 1 times 10 to the minus 8. Then we can compare Q to K. K for lead iodide is 9.8 times 10 to the minus 9. So Q is greater than K. Does it precipitate form? Yes. Good. Okay. For the silver, we're going to have 0.010 for the silver concentration, 0.0010 for the iodide concentration, and we'll end up with 1 times 10 to the minus 5 for Q. Compare Q to K. K is 8.5 times 10 to the minus 17. So Q is certainly greater than K. And again, it precipitate forms. For the tin, we're going to end up with the same Q value as we did for the lead, simply because the ion ratios are the same and the concentrations are all the same. So we get 1 times 10 to the minus 8. Compare Q for tin to K for tin, and we'll get Q is less than K. And so in this case, a precipitate does not form. Okay, so we get precipitates with only silver iodide and lead iodide. And I don't know why I have so many options and half of the time, a couple of them. Okay, there we go. That's why. Yes?
For the lead, or what's PB, what's the?
Yeah.
Okay, for PBI I2, right?
Yeah.
So the QSP was 1.0 times 10 to the negative 8.
Yes.
But that's less than the KSP that they get. No, wait.
No, it's 10 to the minus 9.
Yeah, never mind.
Yeah. Yeah, so, yeah, Q is greater than K. Other questions on those? All right. Okay. This is a similar problem. Now we have to predict the product. So we have a total of 1 liter of water, okay? We're going to add 1 times 10 to the minus 6 moles of lead nitrate, 5 times 10 to the minus 6 moles of potassium chromate, and 1 mole of sodium chloride. Okay, and we want to know what will happen. Now there's some clues here. We have KSP values for lead chromate and for lead chloride. Okay. So essentially, and given the options, we need to figure out if a precipitate of lead chloride will form and will a precipitate of lead chromate form. And so this problem is very similar to what we've done the last problem. We just need to figure out concentrations. We're given moles, but we're in 1 liter of water, so that's convenient. I might just kind of breeze through this one because there's not too much new here. For our lead chromate, we have lead 2 plus CrO4 2 minus. QSP equals the lead concentration times the chromate concentration. The lead concentration comes from the lead nitrate. For every 1 lead nitrate, we get 1 lead ion. So we have 1 times 10 to the minus 6 moles of that in 1 liter of water. And the chromate, we have 5 times 10 to the minus 6 moles of potassium chromate. It's 1-to-1 with the chromate, again in 1 liter. So that's 5 times 10 to the minus 6. When we calculate Q, we get 5 times 10 to the minus 12. Compare Q to K. K is 1.8 times 10 to the minus 14. QSP is greater than KSP. And a precipitate forms. Questions on that part? All right. For the chloride, PbCl2 in equilibrium with Pb2 plus 2Cl minus. Q is equal to the concentration of lead times the chloride concentration of squared. Lead's just this concentration is just the same as before, 1 times 10 to the minus 6. What's the chloride concentration? 1. 1 mole per liter. And so Q is equal to 1 times 10 to the minus 6. Compare that to our K, which is 1.6 times 10 to the minus 5. So Q is less than K. So no precipitate forms. How do these problems feel?
Wait, why is it 1 for CL?
We have 1 mole of sodium chloride, and it's in a total of 1 liter of water.
Oh,
And 1-to-1.
but that's NaCl, so I was like looking at it, I was like, that's a whole different compound.
It's a whole different compound. So in this beaker, we're going to have the lead nitrate, the potassium chromate, and the sodium chloride. So the lead and the chloride combined, lead and chromate can combine.
So you use that value. Okay, that makes sense.
But let's look at these K values. All right. Let's say we have this. This is real. Now we have all of these things in a beaker. Okay. What's going to precipitate first? Which one of these is the most product favored? Not NaCl, but yeah, that's, I mean, okay, certainly all of that goes to completion. Of the 2 that are slightly soluble, which one favors product more? Yeah, the lead chloride, right? Why? The K value for lead chloride is larger than the K value for the lead chromate. Right? Larger K means more products formed. Okay? So let's say let's do another problem. I think this is next. That's not the end. I'll explain. Okay, so yeah, this is a great point. So we said in this problem that lead chromate will form a precipitate, and that the lead chloride won't form a precipitate. How can we make that form a precipitate? Yeah, we add more products, right? Either add more lead or add more chloride. Let's see, what's our K? If we were able to add enough chloride to make Q greater than K, then we would be able to form precipitate. So now, does that help? Not yet. Let's do the next thing and then we'll come back. Let's go back. So the lead chromate is going to precipitate out in this solution, right? K is small. We calculated that based on our concentrations given. Still with these concentrations given, the lead chloride won't precipitate. However, if we were to add more chloride and beef that concentration up, eventually we're going to get lead chloride to precipitate. So now that you've seen that fractional precipitation, we can calculate the concentration of chloride needed to make lead chloride precipitate. And so we have our KSP, 1.6 times 10 to the minus 5, equal to the lead concentration times chloride squared. Our lead is 1 times 10 to the minus 6. Let's do this. Look at how beautiful that is. So we would need to get a concentration of chloride up to 4 molar to start precipitating out that lead chloride. Does that help explain it? Other questions? This is challenging, yes.
So the process of finding KSP is the same as finding the process of QSP?
Yes, so QSP and KSP are mathematically the same formula, but for QSP, you don't know if you're at equilibrium.
Okay.
Yeah.
Okay.
So you're trying to see, say, in this case, when we say we're not at equilibrium, we don't know if we're at equilibrium, it's equivalent to saying, will it precipitate for? That's mainly the question you're going to see. Other questions? Okay. Let's do a different problem. This is introducing us to this topic of fractional precipitation. This is a method that people use to separate ions from other ions in solution. And basically, we add a reactant that will precipitate out one ion with that, like a chloride, like a lead chloride first, before the others. Yes?
So I'm confused because you just said that now it will form, and then you said what will form first.
Yes.
That makes no sense.
Fair. I'll go back. Okay. So in fractional precipitation, imagine you have a beaker and we'll say we have silver ion and lead ion. Okay? We're going to add sodium chloride to those. Silver chloride and lead chloride are slightly soluble salts, but they have different K values. And I don't remember them off the top of my head. But one of those salts will precipitate before the other. The one with the smaller K value will precipitate first. Okay? And that's a physical property that we can take advantage of that allows us to separate ions in solution. Okay? If we wanted to separate silver and lead, we could precipitate out one of them first. Once we can remove all of that from solution, we could precipitate out the other ion. So here's an example. We have a solution containing 0.2 moles per liter of calcium ion and 0.2 moles per liter of magnesium ion. we add potassium oxalate to precipitate each ion individually. So for calcium oxalate, our KSP is 2.3 times 10 to the minus 9. And for magnesium oxalate, it's 8.5 times 10 to the minus 5. So based on those K values, which one will precipitate first? Calcium or magnesium? Did I say it backwards last time? Is that why we're all confused? I'll take the blame. The smaller K precipitates first. Okay? That's more reactant favored. And if it's more reactant favored, that means it forms precipitate because that's the solid. More solid present. So in this example, calcium oxalate will precipitate first. We can prove that mathematically, which I'm sure you're all pleased with. We can calculate the concentration of oxalate that is needed to precipitate calcium oxalate. Okay? And we can use that with the K value and a known concentration of calcium ion in solution. All right? So based on our calcium oxalate, I'm going to set up our equilibrium just at the end of this sentence here. Calcium oxalate is going to be in equilibrium with the calcium ion, 2+, and the oxalate ion, 2-. And so our K value, KSP, which is equal to 2.3 times 10 to the minus 9, it's going to be equal to the calcium concentration times the oxalate concentration. From this problem, it was stated that we have 0.2 molar calcium. And we want to figure out the concentration that's required of oxalate that's required to precipitate that 0.2 molar. That's effectively saying what concentration of oxalate is needed to reach equilibrium. Because right at equilibrium, we're going to start forming precipitate. If we add more oxalate, more precipitate forms. Right? So the concentration that is required, that's the minimum concentration that's required to start forming precipitate. And mathematically, that means we're solving for this concentration with our K value. Okay? That's saying at equilibrium. So we'll have 2.3 times 10 to the minus 9 equals 0.2 times the oxalate concentration. And solve for oxalate. And we'll get 1.2 times 10 to the minus 8 moles per liter. So we have our beaker that contains calcium and magnesium. We slowly add the potassium oxalate. Once the concentration of oxalate reaches 1.2 times 10 to the minus 8 molar, calcium oxalate starts to precipitate off. That's a really low concentration. Okay, does that make sense? If we add more oxalate, we're going to keep precipitating out calcium. Eventually, though, all that calcium is going to precipitate out of solution. We're going to only have magnesium. And so we want to figure out what concentration of oxalate is needed to precipitate out the magnesium. And so we can solve this the same way, ignoring that we've solved for calcium and ignoring that some of that oxalate has gone away. We're just going to basically ask the same question using a different value for K and for our magnesium oxalate. So our KSP is equal to 8.5 times 10 to the minus 5, which is our magnesium concentration, times our oxalate. In the problem, we state that we have 0.2 moles per liter of magnesium, and we solve again for oxalate. And we'll get 4.3 times 10 to the minus 4 moles per liter. Okay, so what does that mean? If we have magnesium ion solution by itself, and we want to precipitate out magnesium oxalate, we need to add the oxalate until the concentration gets to 4.3 times 10 to the minus 4 molar. Okay. Once we get to that concentration, that magnesium starts to precipitate. Right. If we have both calcium and magnesium in solution, we add the oxalate. We get to a concentration of 1.2 times 10 to the minus 8 molar oxalate. The calcium oxalate begins to precipitate. We keep adding more oxalate. Eventually, all that calcium is gone. Okay. Then we keep adding oxalate, and now we can start precipitating out the magnesium oxalate. Yeah.
I'm still confused.
Okay.
So like, back to the other question.
Yeah.
Was that, you said the smart KSP will take out first, right?
Yes.
Okay. So, did you just say the wrong one for that example, or am I dumb?
You're not dumb, no matter what my answer is. Reaction, all did that. This question, we are skipping. Okay, you don't need to know that one, I've checked. All right, so the last topic here is complex ion formation. So we've seen a little bit of this, and we're going to see more when we get to whatever chapter number later on. Complex ions are formed in solution a lot of the time, or maybe all of the time. They're Lewis acid-base reactions. Okay, so we may have seen this equilibrium show up in our acid-base chapter, possibly, where we have silver plus ammonia forming the silver ammonium complex. And in this case, the Lewis acid is our silver ion, the Lewis base is the ammonia. Again, a Lewis acid accepts electrons, and the Lewis base donates electrons. Okay. When we're talking about complex ion equilibria, conceptually it's important to think about the bonds that are formed between a cation and anion, and many times we're talking about coordinate covalent bonds. So a coordinate covalent bond is a specific type of covalent bond. Electrons are shared between two atoms, but with a coordinate covalent bond, the electrons that are shared come from one species or one atom. And so in this example with the silver ammonium complex, the electrons that are shared are coming from the nitrogen that has a lone pair, and those are forming the bond between the nitrogen and the silver. Okay, so we leave the double two dots between the nitrogen and silver to show that that's a coordinate covalent bond. That's what that's referring to. Okay? So why does this show up in this chapter? Well, why not? We've done everything else. So basically, this type of reaction has equilibrium. And so it's just another type of equilibrium that we see. But we need to think about the forward reaction and the reverse reaction. Okay? And these are going to have different K values. The K sub D is for the dissociation of a complex ion. So that's the second reaction. Okay, where we form ions. And then the formation of a complex ion is given a K sub F value. Okay? The relationship between K sub F and K sub D, because we're just reversing the reaction, is the same as we saw in chapter 15. And so 1 over Kd is equal to 1 over K sub F, and Kf is equal to 1 over K sub D. Okay? Okay. So again, this is not a type of precipitation reaction. All right, separate type of topic. Take a look at our phases here for our reaction. Everything is aqueous. Fill in that last column there. Okay, this is not a precipitation reaction. So let's look at another type of problem here then with this equilibrium. We have 0.1 moles of nickel nitrate. We dissolve that in 1 liter of water. That water contains 1 mole of sodium cyanide. This question wants to know, what is the nickel ion concentration after it comes to equilibrium and forms this complex ion? Okay? So we're going to form the complex ion, form as much as we can, and we want to know how much nickel is left over. There's 2 steps in solving this problem. We need to use both a BCA or a reaction table, and we need to use an ice table. All right? So, step 1. The first thing we do is assume that the nickel ion reacts completely to form the complex ion. And so we're going to take our equilibrium, nickel 2 plus, y'all are chatty today, plus 4 Cn minus, in equilibrium with the complex ion, NiCN, for 2 minus, yes, that still has a charge. Oops, and I made a mistake here. We're going to assume that this reacts all the way to completion, right? That's an assumption that we're going to make in order to make the next step easier. So now we're going to do a BCA table. We know our nickel concentration, or excuse me, we know our moles of nickel. We do moles in BCA. We have 0.1 moles of nickel, and we have 1 mole of sodium cyanide. That should be an N. And initially, or before, we have 0 moles of product. Which one of these is limiting reagents? That's how we decide what we subtract, right? So it's the nickel, it's a smaller concentration. And also, we need to take into account the stoichiometry. This is minus 0.1, minus 4 times 0.1, and then plus 0.1. Does everyone see why I'm doing the minus 4 times 0.1? Is the stoichiometry there? Okay, so we are left with 0 moles of nickel. That's great, that was our intention. We are left with 0.6 moles of Cn minus, and we form 0.1 moles of nickel cyanide complex ion. So really the point of this table is to figure out how much Cn minus is going to be left over. We know that the formation of the product is 1-to-1 just based on this equilibrium, but we need to know how much of all of these species are going to be left over so we can fill out our equilibrium table correctly. Okay, go on to the next page. Step 2 is set up an ice table, and this is for the dissociation of the nickel complex ion. So we have NiCN CN for 2 minus in equilibrium with nickel 2 plus and 4 CN minus. Our ice table, we use concentrations. Conveniently, this is in 1 liter. We have moles on our last table. Everything's in 1 liter of solution, so we can easily convert that to moles per liter. So we're going to start with our 0.1 moles per liter of the complex ion, 0 moles per liter of the nickel, and 0.6 moles per liter of the CN minus. That's all coming from that last line of the BCA table divided by 1 to make moles per liter. So our change minus some amount X for the complex ion plus X for the nickel and plus 4X for CN minus. And so we can figure out our equilibrium line here. So we now need to set everything equal to our KD value. In the problem we were given KF, because this is, okay, so our equilibrium is for the dissociation. Have our complex ion is dissociated into the ions. Our KF is for the reverse reaction. So KD is equal to 1 over 1 times 10 to the 31st, which is 1 times 10 to the minus 31. And that is going to be equal to X times 0.60 plus 4X to the 4th divided by 0.10 minus X. Okay. In these cases, where we're subtracting or adding X, we can assume that X is small. 10 to the minus 31 for our case of D value. And so we're going to end up with K sub D equals X times 0.6 to the 4th divided by 0.1. And if I've done my math correctly, X is going to be equal to 7.7 times 10 to the minus 32 moles per liter. And X is equal to the concentration of nickel left in solution. Questions on that? Bring them on Friday. We'll talk a little bit more.